All right, so yesterday we kind of left off, we were talking about reflection. Okay? Reflection is a behavior that waves show. Okay? It's also a behavior that particles show. And we're going to talk a little bit later on today about some of the wave behaviors that only waves will show. And in terms of how that helped us to prove that light had both particle and wave properties. So for reflection, something we have to understand. I think I mentioned this to you guys yesterday. If you've ever tried to like shine a glare into somebody else's eyes, you know, like reflecting the sun off your face of your phone or off your watch, or something like that, and get them in the eyes, you've used the law of reflection. In order to reflect light and change its direction to somewhere else, you have to understand that when any wave comes in, it's going to go off at exactly the same angle. The law of reflection states that the angle of incidence, that's the angle it comes in at, is equal to the angle of reflection. Okay? How many people in here play pool or have played pool? Can you hit a bank shot? I'm going to show you how. Okay? Hitting a bank shot is not about being a good pool player. I mean, you have to be able to hit the ball straight. Okay? But beyond that, if you can hit it to a spot, you can hit a bank shot. Okay? They're not hard. They just involve sighting properly. Okay? Buddy of mine and I, when we were in university, would sometimes go out to the bar and play pool. And we could run a table pretty much most of the night. Neither one of us were great pool players, but we would let our competition get really drunk. Oh, and then we were also able to hit these bank shots that, once people's playing of pool was kind of, let's say, impaired, they wouldn't play pool quite as well. And so, yeah, we would be able to hit these bank shots, but only because we knew how to set it up. It wasn't about, again, being a great pool player, just being able to hit a bank shot. Okay? Even great pool players don't just go, I'm just going to hit this bank shot. They still line it up. Okay? Here's how you line it up. You use the law of reflection. Okay? So let's say my cue ball is going to start right here. Right? And I want to hit this yellow ball over here. But I can't go directly because the 8 ball is in between. So I'm going to hit it off the bumper and then have it come this way. The trick to a bank shot is hitting the right spot on the bumper. So here's how I do it. I imagine the bumper is a mirror. Now, I don't know if you've ever noticed this, but when you stand in front of the mirror, how far behind the mirror is your reflection? Ask him next time. They're exactly the same distance behind the mirror that you are. Okay? So anytime you see a virtual image of yourself in a plane mirror, as long as it's a plane mirror, not curved, okay, your reflection stands the same distance behind the mirror as you stand in front of it. So, in order to make this shot, okay, you need to sight along a line that puts the reflection of the ball the same distance behind the reflective surface as the ball is in front of it. So what me and my buddy would do is, if we knew one of the other guys had to hit a bank shot, is we would stand at that point with our pool cue like this to make it look like we were leaning on the pool cue, and the other guy would line up the shot on the cue. So my friend, or I, would stand right here, and the other guy lines up that shot by sighting to the cue. And hit that bank shot every single time. Okay? All you have to do is understand the law of reflection. Okay? Because we were both physics guys, we understood that the angle of incidence equals the angle of reflection. Okay? And we can make that work every time. Next time you get a chance, try it out. It'll work. As long as you don't spin the ball. If you don't hit it pure and it spins, then it does stuff weird and it comes off. Okay? If you just roll it to the bumper, okay, it'll hit the bumper and come off. It has to. It has no choice. Okay? It's the law of reflection and it must be obeyed. And see if you're going, I'm so trying that. Okay? That's how it works. It'll always work. Okay? If you do. Making sense? Okay? Waves do the same thing. Waves and particles both obey the law of reflection. Whatever angle they come in at, is the angle they come off at, even on a curved surface. Okay, even if it's a curved reflector, the law of reflection still applies. It's just that rays that are coming in are not hitting a flat surface anymore. The next ray over is going to hit, and it's going to go off at the same angle, but because it's curved, it traveled further, and that's how you get magnifying effects of curved mirrors. Okay, if you have one of those like makeup mirrors at home, okay, it's a concave mirror, and it makes a virtual image of you greatly enlarged. Okay, behind the mirror. Okay, that's how it works. It's just got a curved surface that makes a virtual image, behind that's enlarged. If you're looking at those shoplifting mirrors, sometimes they have those. Okay, or they have one. Which bank is that? It's by OPA, in that power center over there, by the Co-op gas bar and that, and the drive-through for the bank. Yeah, it's got a mirror, a curved mirror, so that the people coming out of the drive-through can see if any cars are coming, because it's kind of blind. Okay, if you have a convex mirror like that, it gives you a greater field of view. Okay, because of its curved nature. It still obeys the law of reflection. Okay, it's also your passenger side mirror is also a convex mirror. Okay, that's why it always says on your passenger side mirror, objects in mirror are closer than they appear. Okay, it's because it's slightly curved to give you a greater field of view on that side of the car.
I was going to ask why you just answered.
Yeah, just because you don't see, like that's the side that's further away from you, so there's going to be more potential for blind spots when you have to look through the car to that side, whereas on your side you can shoulder check, you're closer, it's easier. Okay. Most cars now come with like a smaller kind of shoulder checking mirror. Okay, you should still shoulder check, but like for example, my pickup truck has a regular mirror, and then it's got two smaller curved mirrors in the top corner that give me a greater field of view on now both sides. Okay, so when I'm changing lanes, I still shoulder check, but I can see in that mirror that I can, that there's nothing there. It's especially important if you're towing something, you have a greater range of view. Okay, does that make sense to everybody? Okay, I'll show you a couple of videos here on reflection. We said yesterday that properties of a wave change when it enters a new medium. Speed changes, wavelength changes, amplitude changes, and direction can change. Okay? Reflection is an example of waves changing direction. Okay? They're reflecting off a surface. Okay? They don't go into that new medium, they just reflect off of it. Okay? And we can change their direction because of that. All right? Now, when a wave gets transmitted, okay, this is what we were just saying, the transmitted wave will always be upright. Okay, so if I've got a crest coming in, it'll be a crest in the new medium. The transmitted wave is always the same as the incident wave. Okay? Frequency remains the same, controlled by the source. The velocity will change because it's going into a new medium. The wavelength will change because it's going into a new medium and has to change if velocity changes. Amplitude also changes, okay? But again, it's not a hard and fast rule about what it does, okay? Does it always get bigger? Does it always get smaller? There's not really a hard and fast rule on that, okay? It kind of depends on the situation. If a lot of energy gets lost at the reflection, then the amplitude is going to be smaller, okay? Or if not a lot of energy is lost, but the wave slows down, it can be compressed, and then as a result have a higher amplitude. There's no hard and fast rule on what happens with amplitude, just that amplitude does change. It's a property of waves that can change when it goes into a new medium. Okay? All right, and then wave rays, they kind of showed that with the waves. Instead of drawing a whole bunch of waves like this, which kind of is cumbersome and it's hard to look at, you can represent a train of waves with a wave ray, which is just an arrow drawn in the direction the waves are traveling, perpendicular to the crests. Okay, and so that's all a wave ray is. Okay, it's just a line that shows us which way the waves are going. Right? The normal line, and again, this is just terminology, a normal line is always drawn perpendicular to the boundary. The only reason we have a normal line is if there's going to be a change in direction of the waves, either due to reflection or refraction. That's the other one that can change the direction a wave travels. Okay? And so that just allows us to have a reference point to measure the angles from. Okay? All of the angles are measured from this imaginary normal line. Okay?
So whenever we are asked to calculate an angle that, like let's say we're asked to calculate an angle of incidence, it would be X amount of degrees from
from the normal. You will never be asked to do that in physics 20. Okay? We used to do Snell's law in physics 20, but now it's in physics 30. So then you'll be asked to calculate angles based on Snell's law. All right. And then obviously the law of reflection says that the angle of incidence equals the angle of reflection. Waves coming in, okay, waves go off, but they're always going to have the same angle. Okay, now refraction happens because waves come into a boundary at an angle. When they reach the new medium, their speed and wavelength change. Okay, now refraction works differently depending on whether you're going from fast to slow or slow to fast. Okay, in this case, are those waves, let's say they start in the white and go to the turquoise, okay, are they going from a fast medium to a slow medium or the other way around? How do you know?
Because if the line represents the crest or troughs, they're closer together.
Exactly. This is going from a fast medium to a slow medium, and we can tell that because the crests get closer together. In other words, the wavelength decreased. And if the wavelength decreased, that means the speed decreased as well. They have to go together for frequency to remain the same. Okay? So, if I have my normal line that they were talking about before, okay, it would look like that, perpendicular to the boundary. Okay? My incoming or incident waves are going this direction. My refracted waves are going this direction. They bent towards the normal. Waves that slow down bend towards the normal. Okay? And the reason they do that is because you can see in this first wave right here, this part of the wave right here encountered the new medium before the rest of the wave. So it slowed down, but the rest of the wave kept going fast because it wasn't in the new medium yet. Okay? As more and more of that wave get into the medium, it's getting pulled and slowed down, which causes it to turn. Yesterday I gave the analogy of if you're walking along with your arm stuck out and your arm hits something, it causes you to rotate. Right? Because this part of your body slows down, but the rest of your body wants to keep going the original speed, and it causes you to turn. Okay? The same thing is going on here. Part of the wave is being slowed down, but the rest is still allowed to go, so it turns the wave. Okay? And it bends it towards the normal. Everybody with me there? Okay. If I reverse that situation, okay, now the waves start in the blue, or the turquoise, and they go to the white. Okay, so here's my incident waves. They're going this way, but my refracted waves are going this way. They bent away from the normal. They sped up. The wavelengths got longer. Okay, and the same explanation is still true. Okay, when this part of the wave got into the new medium, it sped up and tried to run away from the rest of the wave, which caused it to turn and go the other way. Now this is what gives you trouble if you're spearfishing. I think I mentioned this yesterday. Okay? If I'm spearfishing, my eyes and brain understand that light travels in straight lines. Okay? So I see the fish here. That's Tara. Okay? The fish is actually here. Okay? But my eyes perceive it to be somewhere else. Just like in the video we watched with the magic trick, our eyes perceived the image to be straight ahead. But in actual fact, it was over there, reflected off of a reflective surface. Okay? But our eyes always understand that light travels in straight lines. Okay? So we see it somewhere else. Are you okay with that? Okay, I'm going to show you some refraction stuff. What are some examples of uses of refraction? Glasses. Okay, we have curved lenses that change the focal point of our eyes. The light comes in and its path is already being altered, okay, because our eyes are maybe not the right shape, okay, and if our eyes are not quite the right shape, then our focal point is not on the optic nerve, okay, and so everything appears blurry. Okay? So we get glasses to change the path of the light before it gets to our eyes. okay? And that can help us to see better. What else?
Optical microscopes or telescopes, binoculars.
Yeah, anything with lenses, right? Anything where we want to alter the path, for sure. Anything else? You probably use it a lot when you're at home. And you use it with a lot of devices in your house. Okay, camera's got a lens. Yeah, wasn't what I was thinking of. They just finished putting this in everywhere in town, what, 2 years ago? 3 years ago? Anybody have their yard dug up so that they could put in the fiber optic cables? Okay. Fiber optic cable is how we can transmit digital information really, really fast. It's glass fibers, okay? And they can carry way more information as pulses of light than a copper wire can carry as pulses of, or changing currents of electricity. Okay? But fiber optic uses, again, light traveling through a glass fiber. Okay? That glass fiber can be bent all over the place, okay? And it'll still follow it. Okay? And so it's much faster for transmitting information.
So if you got two people, like one person with perfect 20/20 vision and one nearsighted person, and you got them both to stare at the sun, the person with the better vision would go blind first because the sun would be focused on their optical nerve that.
I guess theoretically, yeah. I'm not about to go try and
Meter 530 experience.
All right, is everybody good with refraction and how that works? All right, and so this is what we were talking about before with going from fast to slow. The waves bend towards the normal, okay, and the wavelength gets shorter. Okay, if we're going from air to glass, that's going to be from fast to slow. It's going to bend towards the normal. Okay, air to water, same idea, but in this case, we actually have water to air, where it would bend away from the normal. We would perceive the fish to be here at the top position when it's actually down below. Okay, beam of light going into an aquarium, okay, will bend towards the normal. Okay, we can see that here as well, okay, and you can actually see it here. So these are, I mean, they look straight. They're probably not perfectly straight, but the waves out here in the deeper part of the ocean are quite straight, okay, but out here, okay, they're getting bent because this part of the wave is getting close to the shore where the depth is decreasing, and it's causing the wave to fan out. It actually makes it so that the wavelength out here looks longer because it's turning the waves like this, okay, because here close to the shore, they've been slowed basically to a crawl, all right? So it's kind of having that focusing effect. When we were watching that video with the big wave surfing, okay, kind of the same idea. You get that wave to turn and come into focus, okay, you can get the amplitudes to be really big. All right, now diffraction. I don't think this is in your notes package, so you're going to need to add this in. Okay, this one's the super important one that separates waves from particles. All right, so if you guys can copy down what's on here and kind of give a rough drawing of what's here. Don't worry about trying to draw this picture, just this diagram here. All right, I'll give you a few minutes to get those down. Okay, so diffraction happens in two different situations. If waves have to go around an object, or if they have to go through a narrow opening. Okay? Doing either one of those things will cause the waves to change shape as they bend around or bend through the opening. Okay? So in this case here, we've got somebody who's at a concert and they got like the worst ticket. Hopefully they didn't pay a lot of money for it, but they're behind this post. Okay, the post is like directly between them and the source of the sound. Are they still going to hear the concert? Yeah, they won't see the concert, but they'll be able to hear the concert because sound waves, when they encounter the light post, are going to bend. They're going to diffract. Okay? Yes, they'll be slowed down, okay, as they go around it, but they will eventually get around it and come back together on the other side. There'll be a bit of a shadow there, but eventually the waves go back together with kind of a small dip in them. Okay? They do this around all objects. Okay? It's why it's exactly the same situation. If I stand behind somebody and there's another person on the other side talking, I can still hear that person. And it's not about reflections off the walls, the sound waves just diffract around the object. Okay? They also do this through a narrow opening. Okay? But diffracting through a narrow opening can take a straight wave and turn it into a curved wave. Because only part of the wave gets through the opening, and it drags on the edges of the opening. So it slows down the edges of the wave, causing it to become semicircular. Now, it doesn't necessarily look like this right away. There's kind of a cone that gets formed, okay, where we would have the waves doing this, right? There would still be areas where I wouldn't get the waves per se. Like, for example, standing here, if someone's out in the hallway talking, I can hear them. But Ian and Cohen probably can't as well, because the sound is coming through the door, which is a narrow opening for sound waves, and it's diffracting. But they might be in this area here where that diffraction isn't fully in effect yet. Okay? They might hear the reflection off of the walls, but they're not going to hear necessarily the original waves of the sound, because they would be in this area where it hasn't diffracted to yet. Okay? Everyone kind of follow me there? Okay, now, the properties of the waves affect how much the waves diffract. Speed and wavelength affect how much a wave diffracts. What do you suppose diffracts more? Fast waves or slow waves? Slow waves, yeah. Okay? And the reason is they're in contact with the thing they're diffracting either around or through for longer, because they're moving slower. Okay? So they actually diffract more. So the slower the wave, the greater the diffraction. Sound diffracts very, very well. I mean, 332 meters per second seems fast, but it's actually pretty slow. Okay? So sound waves diffract a lot. Water waves, which are even slower than that, diffract a huge amount. Okay? And so we can see that very, very clearly. Okay? That means the same is true for wavelength. Longer waves, which are generally slower waves, will diffract more than short waves. Okay? Because they'll be in contact with either the opening or the object for longer, and thus the opening of the object will affect their shape more. Okay? So slow, long waves diffract a lot. Fast, short waves diffract less. And therein lies the problem with light. Light waves are not only extraordinarily fast, they're also extraordinarily short. Okay? And so, for a very long time, scientists said light cannot be a wave because light doesn't diffract. And people are like, well, why can't it be a wave? And they would say, look down. You look down and you see that thing that follows you everywhere. Right. If light was a wave, why do you have a shadow? Waves diffract. Nothing should cast a shadow if light's a wave. Okay? If I have this door open and all the lights are off in here, there's a cone of light that comes in from outside. Well, if light's a wave, that shouldn't be. The whole room should be lit up because light should diffract as it comes through the door. But it doesn't. Or so people thought. The problem with being able to observe the diffraction of light was that people didn't understand just how fast light traveled and how short the waves were. And it does actually diffract, but only if you set it up right. Okay? So, it took a guy named Thomas Young who came up with Young's double slit experiment, which people laughed at when he told them what he was going to do. Because here's what he told them he was going to do. He said, I'm going to take a light source here, and that light source is going to make waves, light waves. And they're like, light's not a wave, dude. I was like, no, trust me, I got this. He said, here's what I'm going to do. I'm going to have these light waves go through an incredibly small opening. Light's a particle. No, trust me, I got this. Okay? He said, they're going to go through this incredibly small opening because I think that light is a wave and that the waves are really, really short and travel really, really fast. Of course, at that time they knew light traveled really, really fast. They had done experiments to try to measure the speed of light. okay? Like, I think it was Newton who tried one where he had his assistant stand on a hill, like several kilometers away, and they would open lanterns, and they would try and time how long it took the light to get to one, like it was ridiculous. And so it ended up being an experiment with a rotating mirror, like an 8-sided rotating mirror, and using like one of the moons of Jupiter when it would appear and when it was supposed to appear, and the timing of that, and we were able to get like rough measurements. Okay, so he said, I've got this narrow slit, and then I'm going to have these 2 slits. Now I'm greatly exaggerating the size of the slits and how far apart these 2 plates are. Okay, they're really, really close together. Okay, and people looked at that and they went, "Did you get dropped on your head? You know what's going to happen here? Nothing. The light's going to go through this opening in a tight little beam, and that's where your experiment will end. Man, are you ever dumb?" Okay? And Young said, "Nope, I know what I'm doing." Okay? Well, here's what's going to happen. People kind of stopped listening to him at that point. Okay? But he said, you know how if you have 2 tuning forks, kind of like what we did the other day, okay, and I set them up, they're 2 sources of waves, and there's spots in the room where there's sound, there's loud sounds and quiet sounds, constructive and destructive interference. Waves interfere with each other. People are like, well, light doesn't do that. Okay? He's like, nope, light does. Here's what's going to happen. I'm going to get waves that will diffract out of each opening. Okay? And I'm going to put a screen a certain distance away. And you know what I'm going to see on that screen? Bands of light and dark. It'll look like a zebra. Bands of light and dark. Because what's going to happen is, on the screen, there will be places where there's constructive interference, places where there's destructive interference, places where there's constructive interference on the screen. And he went as far as to say, based on the wavelength of light that I use, I can predict where the light and dark bands will be. And they're like, you so stupid. That is so not going to work, okay? Because light's a particle. He set this up, turned it on, zebra on the screen, bands of light and dark. Okay? Proved unequivocally the only way light could have gotten through this apparatus is if light was a wave. And it bent as it went through these openings and diffracted. Okay? So what he had was the light got through here and diffracted. Okay? And then it got to these openings where it diffracted again and set up what we call a 2-point interference pattern, just like what happened with the tuning forks.
Can you just use 2 separate light sources?
The problem with that is that the light wouldn't work as well. He needed it to diffract first and then diffract again. So, yeah, you're right. I mean, theoretically that should work, but for some reason it didn't work as well as when he did it this way. Okay. Yeah, so does that sort of make sense to everybody? Okay. So instead of getting nothing, or if he just used this, 2 beams of light, which is all that would have happened in that situation as well, okay, he got better results. Okay, he got it to show that light is in fact a wave, okay? That it does in fact diffract. Okay? Now, the problem with that is that wave is also a particle. That's the wave-particle duality of light, okay? Because the other part of waves is, how do they get here? Waves require a medium in which to travel, yet they travel through the vacuum of space from the sun to the earth. Well, the only way they do it is that they're their own medium, made of photons, and the photons have wave properties that allow them to oscillate up and down, and that allows waves to travel through the vacuum of space. Okay? Everybody all right with that? Okay? So we thought for the longest time that light was a particle because we couldn't observe it diffracting, because it didn't diffract enough over a distance of like from me to the floor for my shadow to be noticeably different from me. Okay? Or an open door having a tight beam of light coming through it, okay, it didn't diffract a lot over that small a distance because the waves are really small and the speed is really, really high. Okay? It had the 2 properties that made diffraction difficult to observe. All right, everybody with me on those? Making sense?
So do photons, they move up and down at the speed of light, I imagine.
Like-
No, their oscillation, their frequency of oscillation has to do with the wavelength of the light.
So,
Not that they're oscillating at the speed of light, but they're traveling from A to B. The waves are traveling. It's hard to
Okay.
explain.
so do the photons themselves
Travel at the speed of light, yes, they do.
So is that like an oscillating, or are they like moving?
Both.
Gotcha.
Yeah, that's the wave particle duality of light, right? Like if you've got waves, light waves incident on a solar panel, okay, well, they're coming through, the air is not what's hitting the solar panel and causing it to generate electricity. You've got the energy of these photons, which are essentially massless particles, like they hit it at an incredibly high rate of speed, and then there's this whole work function and the Compton effect and whatever that causes a current to be generated from that. Okay? That can't really be explained if light is just a wave. It has to have something that carries its energy besides the wave. It's a whole complex thing, but it does obviously show both waves and particles. Yeah. Okay. So from there, I would like you guys, there's just a worksheet I want you to work on that has some stuff on wave behavior at a boundary, reflection, interference, stuff like that. Just a few questions that are kind of like what I would ask on an exam. Okay, and it's in your digital workbook. And it's here on page 4. So kind of near the bottom of page 4 and then continuing on to page 5. Okay, it goes up to question 11, and these are all the kinds of things we were looking at in class. There's some interference questions here in 10 and 11. Okay, there's some wave behavior at a boundary kind of stuff. Right, there's a 2-speaker question. Number 11 is a 2-speaker question. Okay, yeah, so it's basically got a bunch of stuff that we've been talking about over the last couple of days. Okay, so you can get to work on that, and if there's any that give us trouble, we'll go through them. Hopefully we'll get a chance to kind of just go through them all real quick.